Let us start lecture 25. In last lecture, we started looking at the informations what phase diagram cannot give. The first thing is I took a reference of steel. We started looking at microstructure of hypoeutectoid steel if we start cooling it from gamma region, and we started looking at three situations. One is furnace annealing, that means we keep the sample inside the furnace and then hold it there and put the furnace off. Second is take the sample out from the furnace after doing austenitization and then keep it in air so that the cooling rate becomes faster, we call it normalizing, and then that time we see that microstructure becomes finer, but both in case of annealing as well as normalizing we get to see a polycrystalline proeutectoid ferrite plus lamellar pearlitic colonies. But in case of normalizing we see that the microstructure becomes finer as well as the interlamellar spacing in the pearlite also decreases, that means it also becomes finer. So, if that structure becomes finer as well as interlamellar spacing decreases, then the hardness goes up, because whenever we have finer microstructure we have a higher grain bound regions, as well as if we reduce the interlamellar spacing of pearlite, then the cementites are coming closer. So, hardness is nothing but the resistance to penetration. So, if I put a penetrator on the sample, this penetrator is also accessing more number of grain boundaries as well as cementite lamellas. So, the hardness would automatically go up, but the structure becomes entirely different when I do quenching, and that time we get martensite, and the martensite is a kind of needle like structure, and it becomes very hard if we take hardness of that. But this martensite is not mentioned anywhere in the phase diagram, because the phase diagram talks about the equilibrium phases, it does not talk about non-equilibrium phases like martensite. So, phase diagram cannot tell us what could be the morphology, what could be the non-equilibrium phases that could appear. And if we like to see a non-equilibrium phase information in the phase diagram, then we would also we would also need to have a complete information of those non-equilibrium phases. Then we can have a kind of mention in the phase diagram, but that time that phase, the new non-equilibrium phase that would appear, which we also call it metastable phases, would have a separate metastable equilibrium line in the phase diagram. So, that would appear, that we would discuss that part when we will talk about phase diagram of aluminum copper system, because in aluminum copper system we have three metastable phases before we get to have stable Al2Cu precipitate, and those sequence of transformation is basically the supersaturated alpha, which convert to a slightly supersaturated alpha plus GP zone, and then again it would convert to a little lower supersaturation alpha plus theta double prime, which is another phase, which is metastable phase, and then the next transformation would be again alpha with a little lower supersaturation compared to the previous transformation product of alpha, plus theta prime is another precipitate, and then finally we get equilibrium alpha with no supersaturation, rather we have a saturated copper in aluminum matrix, as decided by the equilibrium phase diagram, and Al2Cu phase, which is the stable precipitate. So, for all those phases, metastable phases, we can draw equilibrium situation as per the free energy composition diagram, and we can also plot those situations in a phase diagram. But that would appear when we talk about aluminum copper system. But in case of aluminum iron system, iron carbon system, we do not see the information of Martensite in phase diagram. So, Martens phase diagram cannot indicate those things. So, in order to know that, we need to take help of TTT or CCT diagram, because the TTT and CCT diagram would also include that at a different temperature and different cooling situations, what are the phases and what are the fractions that would appear. And depending on that, there are many heat treatment practices that have been developed. So, let us discuss those things. So, first thing is what phase diagram cannot tell. One is with different cooling rate, phase diagram cannot predict phase fraction, phase morphology, metastable or non-equilibrium phases. So, these are the information it cannot give. So, these are the negative or not negative, the deficiency of phase diagram. Now, since we have talked about steel and we have talked about the microstructure of hypoeutectoid steel, let us get into the microstructure of Pearlitic composition as well as hypereutectoid compositions. The Pearlitic compositions, because if I draw the steel phase diagram, this is 2% carbon and this is 0% carbon. This is 1147 degrees Celsius, 910 degrees Celsius, 727 degrees Celsius. This is composition is 0.025, 0.8% carbon. So, these are weight percent carbon. Now, if I take a composition this, at this point it will be entirely austenite. So, if I try to see grain structure, it will be like this. This is entirely austenite grain and of course, polycrystals. Now, if I reach there, I would have Pearlitic transformation of 0.8% austenite. So, I would get a structure like this. And interestingly, you notice that Pearlite, whenever there is a particular sequence of lamella, we can say that this is one sequence. If I try to pinpoint that sequence, this is one sequence, this is another sequence, this is another sequence, this is another way of distribution. So, now you see that there are blocks which have almost a kind of parallel distribution of cementite and ferrite lamellars. But there is no as such grain boundary. We call these regions are as colony of Pearlite. And interestingly, Pearlite is a mixture of phases, and those phases are nothing but alpha and cementite. So, it does not have grain boundary. We cannot say that this particular distribution of pearlite colonies, particular distribution of ferrite and cementite, these zones we cannot call it as grain, rather we call it as colony, pearlite colony, and the pearlite is not a phase, rather it is a phase mixture of alpha and cementite. So, this would be the microstructure we would get. And depending on the cooling rate, if we have a higher cooling rate, then the pearlite colonies would be finer because there will be more nucleation, and then gradually we have a closer distribution of ferrite and cementite lamellae. So, overall the microstructure becomes finer, so the hardness would be much higher than a sample of 0.8% carbon steel cooled at a very slow rate, that means the furnace cooled. So, normalized structure would be much finer. So, this normalized structure can also somebody can increase the fineness. For example, if somebody does normalizing in open air, and if somebody does normalizing in front of, let us say when somebody is doing normalizing, that means the open air cooling, if I put a huge fan in front of it, so that means I am trying to take the heat out little more quicker than normal holding the sample in air. So, that time it will also increase the fineness. So, gradually the hardness would increase. So, we have a control over it, means I can increase the cooling rate depending on the requirement what particular microstructure as well as associated properties we need. Now, when we talk about a composition, let us say 0.9% carbon steel. Interestingly, here at this point it will be entirely, at this particular point it will be entirely polycrystalline gamma grains, but when I come to this section, this particular region, I would have proeutectoid cementite plus remaining gamma with a different composition. For example, if I do this, so this would be the composition of gamma, what would be there at this particular temperature, and the cementite would have composition somewhere on the right side, because if I try to draw a line here, if I indicate that this is 6.67% carbon, which is the carbon concentration in cementite. So, this would be the composition of the cementite, and the amount of proeutectoid cementite would be this much, and amount of gamma would be this much of this composition. And finally, we will get to this point, because as we are cooling down, finally the remaining austenite is reaching 0.8% carbon. So, once we go below eutectoid temperature, this remaining gamma with 0.8% carbon will convert into alpha and cementite as per the pearlitic transformation. So, we have pearlite plus proeutectoid cementite, and the microstructure, final microstructure would be, so if, so this would be so this region, so I just put it a black field region. This would be cementite, and these are pearlite colony. So, this would be the microstructure if I try to see 0.9% carbon steel. So, now interestingly I could see that the microstructure is changing as we are going from hypoeutectoid steel to hypereutectoid steel. So, this information also is not available in the phase diagram. So, in order to know that, we have to take help from TTT as well as CCT diagram. Let us say I draw a time temperature diagram for hypoeutectoid steel. So, hypoeutectoid steel, I have this is my alpha plus gamma, this is gamma, and this region is nothing but alpha plus pearlite. So, this is a typical TTT diagram for hypoeutectoid steel, and where this is my MS temperature and this is my MF temperature, means martensite start and martensite finish. Now, in this case I can also put gamma, means if I do not hold it for longer duration, I could have little bit of gamma left, and that gamma, if we cool it, quench it, that gamma can transform into martensite. So, depending on that, we can design different heat treatment practices. So, that different heat treatment practices, let us look at the different heat treatment practices, what we can have, common practices what we can have in case of steel. So, if I try to see annealing, so annealing temperature time, so the annealing operation would have a very slow cooling rate. This way is one. Another route could be I can have, I take it to below temperature and hold it there for a long time. So, like that way gradually I can hold it like this, gradually I can hold it like this. So, like this I can have those transformation, and that time we call it as an annealing. Now, if we do normalizing, that time the cooling rate would be little faster. If we indicate the normalizing as this color, different color, this will be my normalizing. So, cooling rate is faster. Now, we can have quenching. The quenching means the cooling rate is the fastest. So, quenching would be like this and then hold it. So, this is, if I put it in green color, this would be quenching, and that time martensite start temperature, the quenching point can cross martensite start temperature, and if it remains in between martensite finish temperature, so I would have martensite plus the remaining phase would be austenite. So, I would have a mixture of martensite plus austenite, and in this case, so in this case I will have pearlite, in this case also I have pearlite with finer microstructure, but here I would have martensite. For example, this martensite start is, let us say 1%, this is 99% the martensite finish. So, if it is between around let us say 50%, so then I would get at this particular condition I would get 50% martensite plus 50% austenite, and in this case I will get. So, now if I drop it further, and then cross this point, then I would get, if I try to see this particular situation, I would get 100% martensite. So, one operation is annealing, second operation is normalizing, third operation is quenching. Now, quenching can be done either in water or oil, depending on what kind of operations we are doing. For example, in case of heat treatment of nuts and bolts or screws, because those structures are tempered martensite structure. So, they are typically it is quenched in oil, because oil has got less quench intensity, means the thermal stresses developed on the surface would be little less, as well as it avoids the oxidation because it is a oily medium. So, quenching can be done oil quenching or water quenching. Now, since we have given example of nuts and bolts, so nuts and bolts, what we do, the process, actual process, because nuts and bolts has a microstructure of tempered martensite. Now, this is a particular term called tempering. This is also an important heat treatment practice. Whenever we form martensite, the martensite makes the surface sample very hard, but it also associated with the brittleness, because it imparts brittleness into the material. So, any brittle material is not good for the actual purpose, actual operation. So, we have to impart toughness into it. At the same time, we have to also make sure that the hardness does not decrease to a great extent. So, if I would like to have a combination of hard sample with a sufficient amount of toughness, then we can follow a heat treatment which is called tempering or called Mar tempering. For example, that case I can have a situation like this. This is martensite start, this is martensite finish. I take it to austenitization, I do austenitization, that means I take everything into austenite and then quench it, and the quenching should be done. If I take this particular reference of this particular, let us say TTT diagram, quenching should be done such that it should not touch any of those C curves. So, it should be quenched like this. So, that means gamma does not convert into any other phase before reaching to martensite. So, if I do that, so I cool it fast, I take it to this level and then I take it to this level, let us say completely martensite formation. Then what we do, we take it to around 500 to 600 degrees Celsius, where this martensite, this is held for some time, and then again it is cooled, and this cooling could be air cooling. Now, when we do this, that time this martensite changes its structure. This martensite converts into, forms some sort of carbide which are called epsilon carbide, and the martensite also forms a modified, a kind of morphologically different ferrite, and epsilon carbide would be embedded on it, and that process would impart ductility into it, but the hardness drops definitely, but it does not drop to a great extent. So, I have a combination of high hardness plus sufficient toughness. So, this is called tempering. Now, there is another operation called ostempering. Now, this is a third practice, this is the fourth practice I am talking about, because we have talked about annealing, we have talked about normalizing, we have talked about tempering, quenching, we have talked about tempering. Now, I am talking about one particular variant of tempering. So, this ostempering situation, if we have a TTT diagram like this, so this is temperature, this is time. In that case, so because this is the nose point and below that we have bainite, and this is another phase which is nothing but ferrite. This is martensite start. That time we take it to the austenite zone, form austenite, and then we quench this one in such a fashion that the temperature up to which we take it after cooling, that one should be above MS temperature, and then we hold it. Let us say I take it to this level and then we hold it and then we quench it. So, in this way what we are going to get is we are going to get bainite plus austenite plus martensite, and these austenite we call it as retained austenite. Since this retained austenite, up to this point I get bainite, the remaining austenite, because at this point everything is austenite, 100% austenite. So, once I get to this level, austenite will convert into bainite. So, and then once we quench it here, so that means I am taking below remaining austenite, I am taking it below MS temperature. So, there remaining austenite can convert into martensite, and there would be possibility, because if we are taking it to if this is MF temperature, and if this temperature is below this particular point, then I would get austenite, little bit of austenite still would be left out, because if all the austenite that was left out at this point would not be able to convert to completely martensite. So, I would have a mixture of bainite, retained austenite, and that is also called retained austenite, and martensite. And this retained austenite has got a huge importance in practical field, because there is a particular steel called trip steel, transformation induced plasticity. That time in this particular steel we have little bit of retained austenite. When there is a crack formation in a structure, around that, at this portion, the retained austenite is, if it interacts with the retained austenite can convert into martensite, so that it can arrest the crack. So, that is what it is called, transformation induced plasticity, and this particular steel is costly, but it has got a very specific and important use. So, that particular trip steel is also coming due to austempering operation. So, this is also an important heat treatment practice in steel. So, let us stop here. We will continue our discussion on heat treatment of steel, and also gradually we will get into the heat treatment of aluminum alloys. Thank you.